Hey guys, this is 6.2, and I believe it is called quadratic expressions. Let's see here. Building quadratic functions to describe situations, part 2. You did the first part yesterday, and this is a 3-part series, and so I've got the middle part. Okay, so let's kick it off with how we finished yesterday's unit with the 16 t squared, and that represents the distance after it falls t seconds. What's the height in feet of an object 2 seconds after it is dropped? Okay, and so you've got, guys, excuse me, you have, your 16 t squared, and the t stands for the time in seconds, and so you're wanting the 2 seconds. So what you're going to do is you're going to replace that with a 2. Okay, and so I get 64 feet. Now, a lot of people would think, hey, 64 feet, that's what, that's how far I fell. No, guys, we can't do that. So we actually need to take the 906 and subtract it from that. And what you're going to get over here, guys, is the 842. And so write that expression. And so just kind of what we did, that 906 minus the 16t squared, because that is how it's going to give us how much it's fell after t amount of seconds. Okay, so we got 18 slides here. So now, guys, we've got our cannonball, and it's shot 10 foot off the ground. So that's why we see at 0, we're at 10. And then it launches it straight up with a velocity of 406 feet per second. So imagine if there's no gravity and that just continues to travel upward, same velocity. So what happens, guys, is that is not going to be a quadratic, that's going to be linear, because what it means is I'm going to start at 10, and every second I'm going to add 406. And so, okay, so if I have 10, I'm going to take plus 406, and so I'm going to get 416. Oops, sorry about that. I'm going to get 416. And so then, guys, I'm going to take that 416, and I'm going to add another 406, and I'm going to get 822. Then we add another 406, and we get 1,228. Then we add another 406, and I'm going to get a 1634. And then let's just do it one more time, and we're going to get 2,040. Okay, and so since there is no gravity, we see there. So again, guys, we started at 10, and so we started at 10, and then we are adding 406 for every second. Okay, and so we can see the line there that it's on. It's a straight line, so that means it is linear. And so if then, guys, we are writing that equation, the distance would be, that 10, which is our initial start, plus the 406t, because the 406t, that is the velocity, how fast we're going every single time. Okay, did I skip a slide? Oh, no. Okay, so guys, now we have, here's the table we've done. Now we have this here that shows the actual height of the ball at different times. Okay, and so the things that I need to know is, hey, I'm looking here, and I see 400, 416, 758, 822, and I would say that the new table outputs are lower than our table from activity 1, are lower than table 1. That could be something that I notice. Okay, I also notice that, hey, for these guys, I changed 406 each time. I changed 380 here, but we see here this is a 358 and those sort of things. And so I noticed too that the rate of change in the new table is not constant. And so, guys, I'm also going to know then here it's not a linear function because it doesn't have a constant rate of change. Okay, now how are they both alike? Okay, well, they both represent distance above ground after t seconds, right? And they both start at 0, 10. That's where it's shot. Okay? All right. So, how are they different? Okay, we said that table 1, we see here, this is that it's in the green. Table 1 has a constant rate of change. All right, let's use, whereas the actual data we see here, it starts the same, but then doesn't increase as much the longer it is in the air. And guys, that would make sense, okay? Think about it. No gravity, I shoot something, it's going to go straight. There's going to be no rate of change, nothing doing that. But we all know, okay, and especially, hey, my hunters out there who are excellent marksmen at deer hunters, is the further away I am from my target, the higher I actually have to aim my bullet, because even with that, the force of gravity is pulling it down, okay? And so I'm going to start off the straight, but then eventually, guys, I will start to curve, and it's going to bring it down and eventually into the ground. Okay, so with this, now we're going to actually write an equation with that, okay? And so, you know, the good news is, okay, you know, we look at this, and what we find out, okay, is that we start at 10. We have that 406t, okay, because, hey, that's my initial velocity, all right? But, okay, we see here, let me see if it shows it on this, okay, the actual effects of gravity, okay, is going to be a negative 16 t squared. That's going to be what gravity is, okay? So if, and we'll start to dissect this a little longer, but again, hey, my launch height, velocity, pull of gravity. That's the three components to a quadratic function when it refers to these and projectiles. Okay, and so here, guys, all right, we have the 10. So what's that represent? Okay, the height. Boy, I spelled that wrong. The height before it was launched. Okay, 10 feet. The 406, the vertical velocity at which it was shot, and then the negative 16t squared, guys, is, I mean, just the pull of gravity pulling it back down to Earth. Okay, that's the three different parts of this quadratic equation. Okay, now how does the negative 16 change it? I'm actually going to go with how IM says it, because I really like the way that they describe it. And it says, you know, before negative 16 changes it, because before the term was added, the height increased 406 feet every second. We saw that straight line, right? After it was added, it decreased how much the cannonball travels by some amount. That amount gets larger each successive second. Eventually, the cannonball stops increasing in height and starts to fall. Okay? It's because, all right, prior to having this whole negative 16 t squared in the equation, the line is linear, right? Okay, but adding negative 16, and again, forgive me, but I am just putting t squared like that for time purposes tonight. But adding that negative 16t squared, the number that pulls the cannonball back down to Earth increases with each passing second until the cannonball will eventually come back down to Earth. Okay, so what that means is, guys, hey, at 1 second, I'm taking 1 squared times negative 16, so it's a negative 16. That's all that it's subtracting it. But then when I take that negative 16 times t squared for 2 seconds, now all of a sudden I'm taking 4 times negative 16, and you get, what, negative 64? So now I'm subtracting 64, but then, guys, it gets even worse. And okay, so now I'm taking negative 16 times, times 9, and that's where it just gets really crazy, and so that amount just keeps building and building and building until after so many seconds, that 406 times time plus 10 isn't bigger than the pull of gravity, and that pull of gravity will eventually overtake it and bring it back down to the ground. So in this one, we have 50 plus 312t minus 16t squared. What do the terms 50, 312, and negative 16 tell us about the cannonball? Okay, so if I'm using these from earlier, okay, the 15th, okay, the initial, spelled that wrong, the initial launch height, right? So it was launched 50 feet in the air. The 312 represents the velocity at which it was shot. So it had 312 vertical velocity. And then the negative 16, once again, guys, is the effect of gravity pulling the cannonball back down to the ground. Okay? That is that effect of gravity. Now, here we got this, okay? And so that we see, guys, it is a parabola, the shape, okay? And so that the distance from the ground increases, then stalls, and I know I probably spelled stalls wrong, I'm sorry, and then returns back down to the ground. What does the shape of the graph tell us about the movement, guys, of the cannonball? Really, guys, just that it was shot into the air and then came back down. I mean, that's really, guys, that's a shot. You go up, down. That's all it's telling us. Okay. What do you think that maximum height is? Okay, I'm looking here. You can click on it to see. I'm saying we're about right in through here. So I'm going to say it looks like it is 1571, that feet there, okay, because that looks like that's about the height. Okay, when does this happen? Looks like it was at 9.75 seconds. When does the ball hit the ground? Okay, so guys, I'm shot here, and we know that it's shot at 0.50. It comes up, I peak, and then I come back down. I know it hits the ground when this y value is 0. Okay, and then I'm going to go here, and we see here that at 19.659 seconds. So guys, 19.7 seconds. Okay, what would be an appropriate domain? Okay, just remember, guys, that's my x value, so like where this would be. And so even though it's shot at 50, we want to start that at 0 because I'm not going to have negative numbers there with that. And then, hey, where does it end? We said that was at 19.659, so 19.7. Or, we can go 19.659 if we want, but let's just round it up to 19.7. That would be your domain. Okay, I believe that was this one. Okay, so now, guys, so far we've seen the different expressions that represent these. Here's 3 expressions that represent distance from the ground in feet as the function. What do each of these tell us? We have this, okay, basically that it traveled, well, let's back up. Represents the distance it has traveled after t seconds, okay? And so the 400 minus the 16t squared, we knew that was the height of the object after t seconds when it was dropped from 400 feet, okay? And then we see here, okay, and this was the height of a cannonball, right? It was the height of the cannonball after it was shot into the air from 50 feet with a vertical velocity of 100, because we see here, guys, the B factor is 100. We know that was been the vertical velocity. This is if I'm at 0, I'm at 50 there, so that's my height. So I shot it, into the air from 50 feet with a vertical velocity of 100. Okay? After, hey, sorry. We're going to be clear. After t seconds. Okay, after t seconds from being shot. All right? And let's not say being shot. Let's say being launched. Okay. If 16t squared defines a function, what does the 0 of that function tell us? Okay, it tells us the distance from the ground after 0 seconds. Okay, and then it happens basically, and it is our initial height, okay, or what you guys remember I always say the starting point, or starting point. Okay, if 400 minus 16t squared defines a function, what does the 0 at the function tells us? Well, hey, it's at 400 minus the 16t squared, okay, and so basically, guys, here it tells us when the object will hit the ground after t seconds. Okay, so in this case, the object will hit the ground after 5 seconds. Okay, that's what that means. What does the zero here tell us again, guys? And so again, it also tells us when the object will hit the ground after t seconds. So in this case, okay, it will hit the ground after 6.715 seconds. Okay, let's do our last slide. Let's do our cool down. Okay, and so we got 5 plus 100t squared minus 16t squared, and the graph that represents the H, which is a stomp rocket. All right, I don't know if you guys used to play with these or not. These things were so cool. Back in the day, you'd put them on there and you'd stomp on it, and that blast of air would shoot the rocket up into the air. Okay, so what's the fight? The 5 represent? It represents the gosh darn it, the launch height, or okay, the rocket was launched from 5 feet in the air. Okay, what does the 100 mean in terms of the rocket? Okay, and that the initial velocity of the rocket was 100 feet per second. Okay, and then what does this represent? And this, guys, is just the effect of gravity pulling the rocket back down to Earth. Okay, and when does the rocket hit the ground? Okay, we see here it is, what? Not halfway. It's after 6. Let's go with an even 6.3 seconds. Okay, so at 6.3 seconds, it hits the ground there. Okay, hey, that's the last slide. You guys have your classwork now. Feel free to reach out if you have any questions. I'd be more than happy to help. Also, make sure that you're utilizing those tutoring times offered after school, both Zooms that are offered. And really, if you're struggling, please advocate for yourself and reach out. So with that, hey, ain't nothing to it but to do it. You got this. All right? Have a great day.